So in the previous section we saw kind of this resonance view of benzene where you take two Kekule forms and there's resonance between the two. And this certainly describes the shape of benzene, but it doesn't describe its reactivity. And so in order to really look at the reason why a benzene is much more stable than a typical conjugated triene, we have to look at the molecular orbital picture of it. And so if we think about the quantum mechanical calculations that obviously we're not going to go over, but essentially they tell us that the six 2p orbitals of each one of the carbons produces six molecular orbitals. And those six molecular orbitals occupy four different energy levels. So we're going to have two sets of orbitals that are degenerate from one another. And we can draw an energy diagram, where we can have some arbitrary spot in that energy diagram that is the non-bonding area. And so what happens is we get three energy levels that are below this non-bonding line, and we get three energy levels that are above the non-bonding line. And in reality, that non-bonding line is about the same energy as that of a normal p orbital. And so here this shows you that when the six p orbitals mix, you end up with three orbitals that are lower in energy, molecular orbitals that are lower in energy, and three molecular orbitals that are higher in energy. And the lowest energy molecular orbital is called phi 1, and then we have phi 2 and phi 3 that are a little bit higher in energy. And that energy distance we could define as for that of phi 1 is 2 beta, where beta is again some arbitrary number. Your textbook talks about this. We really won't get into a lot of detail about the actual energy values, so you don't really need to know them. Just know, but you do need to know, that you have three orbitals lower in energy and three orbitals higher in energy. So the higher energy orbitals are phi 4 and phi 5, and then phi 6 is the highest energy orbital. And of course, as you should be able to predict, the three lowest energy are bonding orbitals, right? Because they're lower in energy than this arbitrary non-bonding area. And then of course the three higher orbitals are antibonding orbitals. Now, when we place electrons, how many electrons do we have? We're only talking about the mixing of the p orbitals. And so we have three double bonds, right, which are creating those pi, so 3 pi bonds. And in each bond is 2 electrons, and so we have a total of 6 pi electrons. And when we place those 6 pi electrons, right, the first go into the lowest energy, and then of course we have 4 left over, so we place them accordingly, and you notice that all of the bonding orbitals now are full. Not only are they full, but they are all lower in energy than your typical pi bond. This explains the inherent stability of that benzene ring.